So we got this little computer. It's a personal one. It's only 2 feet, but as we saw today, it's enough for the beginners. And as you can see now on the big screen, so here we have gates, and we call this computer SPINQ. It's in Slovenian. It means that it's a little one, spin, and it's mostly like a toaster, so it's not very big. And I will ask my colleague Dan to tell more things about it.
Hello, can you hear me? Can you lower your sound level? Hello, my name is Dejan Muzetic. Yes, but it's 3 hours. Hello? I would like to say a few words about the SPINQ computer. It is based on nuclear magnetic resonance principle, which is one of the principles not mentioned in yesterday's talk. It's not one of the mainstream approaches, I believe, mainly because it is very difficult to generalize it to a large number of qubits. IBM at some point made a prototype with 5 qubits. Well, we have 2. It's a good thing to experiment, play with for educational purposes. You cannot expect to solve a problem that would require a classical supercomputer on this. Today, I'd like to just briefly introduce the machine, and next week maybe we'll show some more examples. What you see on screen, well, by the way, those of you who followed the QWorld annual meeting on a week or 2 ago may have seen in the presentation of QGreece a classroom equipped with just this kind of machines. Those who haven't, maybe if I move my webcam, you can get an idea about how it looks. As Alyosha said, it looks like a small toaster. Or some people, upon seeing it, thought of microwave, which actually isn't very far from making sense, because the active sites of the molecule, okay, I'm running ahead of myself, but the computer uses radio frequency waves to communicate with the quantum core, which is a collection of aligned nuclear spins. But I don't want to go too deep into the implementation details. Rather, I'd like to show you, for starters, the simple interface that we can use to compose quantum circuits. The one on screen happens to be a single Hadamard gate. How old is the computer? This one particular is about 2 years old, but the company is, it was actually one of the first ones made by the SPINQ company in China. And they are developing new models. By the way, they also work on computers based on Josephson junctions, cryogenic technology, but their specialty are these nuclear spins. They have a 2-qubit and a 3-qubit model. The circuit on screen consists of a single Hadamard gate, which is what we've seen at the very end of the lecture. If we click on the run button, the execution will proceed, but since it's been processed already, I will just show the results. from the run of a few minutes ago. We see the name of the task, the starting time, the ending times. By the way, it takes about 30 seconds to process one such computation. And we see the summary of the circuit, a very simple one. And here is the Bloch sphere, the representation of the resulting quantum state that we've heard about in the lecture, and I'm sure we'll hear more in the two coming lectures. It's a convenient graphical representation of the state, along with, unfortunately, because of the webcam image, you can probably not read the screen easily, but it says projection probability, and the two bars represent the probability of being in state 1, which is 0.5. Incidentally, for this particular run, it is exactly 0.5 each, though usually it is differs from the theoretical expected value by a small amount, because it's an actual execution, it's not a simulation. Now, I don't want to bore you too much, but I'll show you, since it's a qubit system, and since we had another interesting example just minutes ago that I also ran through. I believe this is, no. Sorry. Okay, maybe. Okay, this is the circuit that was demonstrated in the lecture. One of the qubits is negated by an X gate, and then a C naught, a controlled naught, is applied to it. These are the results. We cannot visualize, since it's a 2-qubit system, we cannot use the Bloch sphere for a nice graphical visualization, but we do have the projection probabilities. And here, this empty space is probability 0 for a state 0, 0. This one, see, now we don't have exactly 50-50, but this one you cannot read, but it is 0.4694, and the other one is 0.530 something. And the last state, the 1, 1, it has probability 0. Now, since I said that this will be a short introduction, just so that you get a taste for it, I will stop here, but I will invite you to ask questions on Discord, and I will do my best to answer. I will also try to upload some high resolution slides, because we're using the webcam because we're having technical difficulties, and I know it can be frustrating. This will be all for tonight. Thank you very much.
Thank you very much.